Hello and welcome. This is Wylker, and today I'm going to be spotlighting a portion of Minefactory Reloaded. We did a preview on this, oh gosh, I guess it's been about 2 weeks ago now. And these are the integrated logic circuits, otherwise known as Programmable Rednet Controllers, and they are a part of Minefactory Reloaded. They're on the surface very simple, but of course, like a lot of Redstone projects, very complicated if you choose to put the time and effort into them. So what I'm going to do is show the blocks and the tools, and I'm going to show some of the more basic, I guess, applications of them. And then I'm going to leave the rest up to you guys out there that are probably significantly better at this than I am. So to get started with, here is the Programmable Rednet Controller. This is what it looks like sitting out in the world. And it's made up of a couple different components. You end up having to make the casing for it, and then you can finish the final portion of it. And when you first right-click it, you're going to see an interface that looks like this. And you'll see there's a list of a ton of different integrated circuits in there. You'll also notice some buttons over here, right? So we've got a previous and a next, and we've got a 1 out of 6 and a reinitialize button. Just so you know, by default, these guys can support up to 6 simultaneous circuits. Then you've got these upgrades, and they're called expansion cards. So here I'll spawn a couple of those guys in, and there's a 100, a 300, and a 500. And you'll see it shows you here in your chat window. What it does is it increases the amount of circuits you can get and the amount of variables you can use. So what I can do is you'll notice here again, there are 6 pages. And if I throw this 100 in here, you'll notice it renders really cool over there on the side of the controller. And then I now have 7 total pages. Whereas if I take a 500 and toss it in there, and again, it renders. It's the details, folks. Now we have up to 12 pages of simultaneous circuits that can all operate. So the most that one of these guys can support, if you fill it with 6 of the 500 level expansion cards, is 36 total circuits and like a billion variables. And I'll explain some of that more as we kind of go on here. So the other block you're going to need to make these guys work is the actual Rednet wiring, and that's this guy right here. And we can use that in place of Redstone, Redstone dust from vanilla. It'll also work in conjunction with vanilla Redstone. You'll see here as I drop vanilla Redstone down, it connects to it via these little interface plates. And just so you know, the way the interface plate works is it's color-coded. So by default, it's going to pop up with a white here. And this, in some ways, it works kind of like vanilla Redstone. And in some ways, it doesn't. Like, for example, there'll be occasional situations where you use the power of 2 system to define these colors. But in most cases, you're not going to end up using that. So you'll notice here that these little blocks appear, these little plates appear whenever I'm interacting these Rednet cables with anything else. So for example, right there, you see it interacting with vanilla Redstone. Here it is hooked up to a lamp from thermal expansion. If I were to put down, I don't know, you guys get the point. So the other part of these plates is that you can change the color that they represent. So you see what I'm doing is I'm using an Omni wrench, but you can also use the sledgehammer from MFR. And as I cycle through it, it's going to change the color. Now, if I break this redstone, okay, and then replace it, notice it kept the color. But of course, if I break the actual Rednet cable, it resets back to white. One of the neatest features about the Rednet cable is that if you place 2 different connected devices or 3 different connected devices, notice each one of them can have its own color. And that's pretty powerful. That means you can have, in each block of Rednet cable, you can have up to what? I guess 5 or depending on how many, connections you have to it, but you could at least have multiples coming out of each one of those blocks. So that's that. So how does this stuff work? Let's go check it out. The first circuit I set up over here is really simple. You'll notice I have AND selected here. And in your interface, you've got your input-output selector, which is a directional selector, and then the color. So you notice if you look on my mini map up there, I'm facing south. So my inputs are from the south. And then I have a white and a orange selected. And I have levers placed over here. And you notice I've changed the plates here to white and orange. And here's my output on the north side, right? So I've got a vanilla redstone lamp there. So you notice this is a basic AND circuit. When I click one lever and then the next lever, ta-da, my light comes on. Spectacular, right? Now, if I wanted to, I could real easily change this over to a OR. And once I do that, you'll notice I get my light with either one, just like you would expect an OR gate to. And of course, I can do a NOR. And those of you that are familiar with these circuits know that NOR gates are pretty useful for stuff like doors. So the next thing I want to show you is, we'll come back to this one in a second. So this is a D-latch. So D-latches are pretty simple. All it means is that, we've got an enabler, which is in this case up here. And then we've got our D input. So you notice on our output over there, if I hit this guy, nothing happens. Once I turn on my enabler, ta-da! And now I can toggle the light with the switch, okay? Or I can lock it into the on position by disabling my enable side. So another pretty simple circuit. Again, I have the south and the up selected over here for my input controls. And you will notice that a lot of these gates also have an inversion output here. So you see this Q sharp. So Q, white north is on, right? Let's shut this back off. And oops. All right. And then if I wanted to, I could put a, I guess we'll use one of these. I could put like, say, an orange, if I can reach it. There we go. I could put like an orange control there and put on my null output to the north side also an orange. So now it looks a little bit like a toggle because it has a null output. So as soon as I activate my signal, it switches over. Pretty darn easy. All right. The next circuit I want to show you is something that has to do with what I was talking about with internal variable controls and stuff. So I didn't really understand this too well. Those of you that are more familiar and play more vanilla will know exactly what I'm talking about. Redstone now carries a strength, right? So what happens here is, you guys know redstone only travels, 15 blocks. So my redstone signal ends right here from that lever. And so what happens is this signal starts from a maximum strength of 15 all the way down to 0, and then it goes away. And Power Crystals has invented a cool tool to allow us to measure this, and it's called the Rednet Meter. And you'll see here when I click on vanilla redstone stuff, nothing really happens, okay? But we know what that signal strength is. The Rednet Meter is designed specifically to work with the MFR Rednet circuits. So let's go take a look at that. Oops. Whatever. So you notice right here I've got a lever with a little bit of redstone, vanilla redstone coming out of it and then feeding into my logic gate or my logic circuit over here. So I'm going to turn this on. And we know it starts at 15, right? So I should have 14, 13, And Rednet subtracts 1 from the power of these signals when it enters the system. And that prevents you from having like infinite loops of Redstone signal power. So now when I grab my Rednet meter and I click this guy, it's going to tell me that white has a power of 12, right? You guys see that right there? Let's see if turning this off helps a little bit, right? Oh, except I'm in creative. All right, just kidding. So when I click that, I've got a white power of 12, and it shows all other Rednet subnets are 0. So if there were other values, it would tell you what they were there also. So then this guy, if we crank him on, we notice we've got a power of 11 there. And I'm going to leave him off for now because I want to show you the next circuit. This is real simple. This is an analog adder. So the analog adder is just going to take however many, the value of each one of your inputs and add them together and just output a result. So let's verify this. So I've got a 12 in, right? And then over here, I've got 12 out. Real simple. Then if I come over here and I turn this guy on, we know I've got 11. And now my output over here is 23. Now what you could do here, like let's say you wanted to add a bunch of signals together, you could you can chain these together on multiple pages. And you know what, we'll get into that here in just a minute. So the next circuit is just the digital version of this, okay? So let's go back and look at this for a second. So you'll notice I have over here, for those of you guys that have worked with binary circuits before, I've got 2 inputs and my carry in, and then I've got a sum and a carry out. Obviously, we're just dealing with 2 bits of data, so I need the carry to help us support the additional option, right? So now that I have nothing traveling through these Rednet cables, you notice I have no lights on over here. Well, if I come and, oh, by the way, I don't know if I showed you guys the output. So I've got my sum to white and the carryover to orange. So white and orange. So my first possible value, which is 1, is now lit up. And then my, what is it on white? Yeah. My second possible value, right, is 2 in this case. And then, of course, if we wanted to, we could use the carry to get us a value of 3. So real simple. Make sense? Great. All right. So the next circuit I want to show you is really a neat concept that you can do a lot of different things with. And what I set up here is just something very basic to show real simply how to operate the circuit, and then you guys can obviously extrapolate from there. So let's turn the sound up for just a minute. I want you guys to hear this. I hope that's loud enough for you to hear it. So what's going to happen here is you'll see this is a demultiplexer. And what this does is it takes a predefined value of 15, and that's what it's going to pass over to these output values, and then it takes the switch direction here, right? So what I'm going to do is I have some dirt blocks here, and what I have is a weighted pressure plate, and I'm going to start tossing them on there. You notice because I have a value of 1, or my starting value down here, 15, that we've got a light on. And as I start tossing dirt on here, you'll notice that my little light tree starts filling up to the top. And once you reach the whole deal, ding, and then of course I can pick them up and it'll reset. So all it's doing is measuring the input from the weighted pressure plate to it takes it and spreads it out depending on how much input there is. So that's neat. All right, let's turn the sound back down. Hopefully you guys could hear that. All right. Next we've got what is this over here? Oh, a one-shot pulse. And so this is neat. And remember earlier when I said I was going to show you how to piggyback some of these signals? That's what we're going to do here also. So you notice I fire a one-shot pulse. And you know what I'm going to do here, actually? Let's replace this. So vanilla lamps have a minimum of 4 ticks worth of input. So this is just going to be a little bit more demonstrative. So see that? When I click it, my toggle goes for 1 tick. And that's all I get. Okay? Instead of the light being on constantly like it would if you, say, had a lever directly attached to it like that. Now what I can do, you'll notice one-shot pulse generates a pulse. Great. So I've already kind of set this up. Instead of outputting to a side like I've done here, I can output this to a variable, and the variables are all internal to the blocks. So you'll notice here I'm outputting the variable 0, and on my next page, I'm actually reading that variable as a input. And you'll notice here I have pulse lengthener selected. So my constant here, the L, is the length, and it's going to lengthen any pulse it receives by 20 ticks. And we're going to go ahead and set the output up, which is on the south here, right? All right, great. So now instead of a 1 pulse tick, I get a 1 tick pulse. I get a 20 tick long pulse, which is about a second each time I flick the lever. But that shows you real basically how you can pass data from one circuit to the next. Now we're going to talk about some of the more practical things. Here's a real simple T flip-flop. You'll notice this is built on a clock edge. So that's kind of the equivalent of enabler for those of you guys that aren't real familiar with these circuits. If I were to set this to a different side, you notice my T is on my east side and the clock is on the east side also. If I were to set that on a different side, it would only register the T when the clock was also receiving power, when it was powering on. But in this case, because I put them on the same side for a basic circuit, you'll notice. What did I do? Oh. Why are those on east? I don't know how that happened. Let's try this again. All right, so now they're on north. So each time I click the button, my lights are going to toggle. Real simple. And if I just wanted, you notice remember I talked about the not output here, so I could turn that off, right? And I have no lights, and I'm just going to get this type of toggle, right? On and off. Pretty straightforward and simple. All right. Next, we have a really interesting device over here, and I'm actually going to wait for it to get dark, and we'll come back. Oh, you know what? We can probably see it. So what this is called a scalar. And what it does is it takes an input and multiplies it to get to your output. So you notice there's a minimum and a maximum. So in this case, I'm going from an input of 0 to 4 to an output from 0 to 20. And all that simply is going to do is take whatever my input signal is and scale it out to my output signal. And we've demonstrated this by just setting up a little path of redstone dust. And watch as I throw my first dirt on there. See that? I now have a signal of 5. And once I break the threshold and get that input up to 2, now I have a signal of 10. And it's 10 because of the scaling I used. So 1 is to 5 as 2 is to 10. And if I were to continue throwing them on here, now I've maxed out my signal because I have an input signal of 15 over there. And that's a scalar. This is an SR latch, right? So set and reset. So you notice set is tied to orange, right? And reset's tied to white. Pretty simple. Okay. Steven's building a project over there that I guess we'll have him tell us about here in a minute. The next thing is a counter. Yeah. Gosh. We had this set up and then we moved it to a daylight sensor. So, okay, here, before I show you that, I'll show you how the daylight sensor works. So we have a daylight sensor set up over here, and it is set up to this 7-segment encoder. And a 7-segment encoder, once again, for those of you familiar with electronics, know that is the little, see this looks real familiar, right? It's the little section of lights that make up like clock numbers, things like that. And you notice right now it's on a D, and that's because the Rednet will recognize signals from 0 to 15. And so we're on what, I guess, 9, 10, 11. Oh, and you saw it just change there, right? So that's, that should be E, right? So it's set up to power the different colored, you see there are lamps we've got set up just depending on what the output is. So yeah, it's real simple. It takes an input, depending on the input value, will power the 7 segments and hopefully give you an accurate output there. I wonder what that was before. I wonder if that was an A, and no, because the A is uppercase. There's the A right there. So, yeah, so there's A. Oh, you know what that was? It was a 9 before. Okay, no problem. So, yeah, pretty neat. This is just the basic light sensor approach to the thing. The other thing you can do is work this guy off a counter. So first, the counter circuit. You notice my increment is on white, my decrement is on orange, and my my preset, where it will reset back to 0, is set at 10 here. And then that circuit, you'll notice, makes a, oh, by the way, there's 2 outputs. So the Q is going to be a pulse output whenever you reach your preset, and the V is the whatever the constant output of the counter is, the value of the counter. So if I wanted to increment this guy, I could with white. See that? I think that's a 5, right? 6, 7, and 8, 9, 0, and then we've got 1, 2, and so on. So it'll just continue counting each time it receives a pulse. So that's how you do a basic counter. I know a lot of people have asked about that. Let's see here. So this is one of the more complicated circuits. This is called a JK flip-flop. And you'll notice I have 2 toggles, the J and the K, as well as the clock, just like on the other toggle we looked at. In this particular case, we're not worried about the inverse. We're just going to try to get our light to turn on. There's a couple states this thing can operate in. The first is our regular on, right? So to turn it on, we need to put power in our J and hit our clock. Okay. Power it on. Now you notice now that the J is on, powering the clock does nothing. However, if I power the K, it will turn it off. And again, flicking the switch causes nothing. However, if both my J and my K are both on, then this will turn into a toggle. So simply sending it a signal will toggle the output. Very useful. How's your project coming over there, Steve? All right. The next circuit I want to show you is another block that I think people have asked a lot about, and it's a timer. So you'll notice there's a couple different waves in here, and I'll show you some of the other ones, but the timer wave allows you to do all of your basic timer functions. And he's piggybacked this into something else I'll show you here in a second. So setting the constant up here for your timer is the amount of ticks that each count of your timer goes. And you notice here, again, he has we have the variable set up to 0. And what that means is that we have some more to look at. And you'll see here, what he's done is set up a ring pass-through. Oh, I say he, by the way. Power Crystals was helping me set these up earlier because I didn't really know how a lot of this stuff worked. So this is a ring pass-through, which means it's going to just go through all the outputs. And you'll notice it's putting out, he told how many outputs there were, so it knew how many to cycle through. And the signal of 15 just means on, okay? For blocks like redstone lamps like this, it doesn't matter what signal output you put to them. But if I were to say replace this with one of these and change this down to like 8 or 7, actually it's going to be hard to tell because we don't have another one of these next to it. So that block is on, but it's on at a lower power than, say, the maximum power can receive. All right. So I promised some more waves. First thing I want to show you guys here, this is really simple, by the way. All I have is a ton of vanilla redstone hooked up to the output of this thing. So I can turn the randomizer on. I have to give it a minimum and a maximum. So let's set this to 16. And now all it's going to do is just randomly generate a pulse. It's a pure randomizer. No, it's not a bug. This is exactly how this is supposed to look at this random. So I think if we see that when it's that high of a value, it gives you a much higher percentage chance of it actually being on. So, whoa, there we go. All right, so there's our basic randomizer. I did promise you guys I'd show you a couple different waves. So let's look at the sawtooth. So here's a falling sawtooth, right? See how it starts at the top, all full, gradually falls in. Then we've got the rising, which is the exact opposite. And of course we have the sine wave, which, as you can see, is a little bit more traditional as far as a wave goes. I don't know what you'd use that for, but it certainly works. And then the triangle wave gives you a similar to a sine wave, but of course it's linear up and down instead of logarithmic up and down. All right, all right. So from a practical standpoint, which I mentioned earlier, we've got a block like this, which is just a real basic XOR setup. And you'll notice we've got it plugged to 2 levers. There's a pink and a pink. Oh, I guess that's orange. All right, so anyway, so orange and pink. And you'll notice there are some white red nets there, and surprise, surprise, they're attached to sticky pistons. And so then I got a real basic usable door that I can move in and out of. Just a real basic XOR. All right. The last item I want to show you here real quick before we go see if Steven has something for us to see is called the PRC memory card. And what this does is it allows you to walk over to a, see here, completely unprogrammed, to walk over to a programmed PRC, right click it, you'll notice I get some status feedback there. And if I come over here and click it again, bam, program downloaded from memory card to PRC. So now, whatever I had programmed in that other one is here now. It lets you repeat circuits and do stuff like that really easily. All right, Steven, what do you got for us? Can we come look? All right. See if I forgot anything. Did we do this one? Yeah. All Yeah. All right. Yeah, Steven, I'm out of things to show him. I got to come over there. So Steven's building a drawbridge or a moat or something. I don't really know. Ah. Hey. Oh, hang on. Steven, I don't think they're not going to be able to hear you. Yeah, it's just type. Oh, okay. Okay, I see. So he's built a combination lock. Here's his circuit. All right. So... Oh, okay. All right. I'm tracking. So you have to know the combination to get it to open is what he's done. So let's take a look at it. Okay, there's our pistons. Oh yeah, I see what you're trying to do there. Okay. So notice we have a bridge. And what's our combination here? Just the yellow one? Oh, right, okay. So there's all off. You guys see we have no bridge through this horrible pit of lava. But if we were to turn them all on, there's 3 of them on. Still nothing. Oh, you turn the 4th one on. Turn it off again. And so there you go. Bridge falls away. When you enter the right combination lock, bridge comes back on. Pretty darn cool. Well, I think that's it. Steven, thanks for your help. Power crystals, even though you had to go to bed, thank you for your help getting this set up. I'm not sure I would have figured all this out on my own. Thank you guys for watching. This has been a spotlight of logic circuits in Minefactory Reloaded. And, oh, by the way, I did hit 1,000 YouTube subs today. So thank you guys so much for that. I'll talk about that a little bit more in my Let's Play that I'm going to record. So thank you guys, and we'll see you next time.